You ever see a massive container ship gliding through the water and wonder, how does it stay so perfectly level? I mean, how do crews make sure it doesn't tip forward or backward while they're loading thousands of tons of cargo? Well, it's not just luck, and it's definitely not guesswork. It's a precise science called trim. So let's get into it. Believe it or not, the core idea behind balancing a 100,000-ton vessel is exactly the same one you learned on the playground. Yeah, it all comes down to managing a giant floating seesaw. If you can get your head around that one single analogy, then everything else we're about to cover is going to click into place.
So here's our game plan. We'll start with the basics of that seesaw. Then we'll get into the master metric that pretty much governs everything. After that, I'll show you the 3 simple formulas you need to solve almost any problem, and then we'll walk through 2 real-world examples, from a simple weight shift to a more complex loading operation. All right, let's dive right in by getting the basic terms and concepts down. Honestly, once you nail these, the rest of it is just some pretty straightforward math.
First things first, the word trim itself. What is it? It's really just the difference in how deep the ship is sitting in the water at the very back, that's the aft, compared to the very front, the forward. If those 2 depths or drafts aren't the same, the ship has a trim. Simple as that.
And you can have 2 kinds of trim. Most ships are actually designed to be slightly trim by stern, meaning the back end sits a little lower. This helps with things like propeller efficiency and keeping the ship stable. Trim by bow, on the other hand, where the front is digging in, yeah, that can make steering a real nightmare, so it's usually avoided.
Okay, so if the ship is a seesaw, it has to have a pivot point, right? A fulcrum. Well, in naval architecture, we call that the center of flotation, or just F for short. This is the exact, calm spot that the entire ship tilts around whenever you shift weight.
So where is this magic point? It's the geometric center of the ship's waterplane. Just imagine taking a slice of the ship's hull right at the waterline. The center of that shape is your pivot point. Every single trimming calculation is measured from this one critical spot.
All right, now that we've got the basics down, let's introduce the single most important number in all of these calculations. This is the key that unlocks pretty much everything. It's called MCTC. That stands for moment to change trim by 1 centimeter. The easiest way to think about it is as the ship's resistance to tipping. It's a number that tells you exactly how much turning force, which we measure in ton meters, you need to apply to make the ship's total trim change by just 1 tiny centimeter. Every ship has its own unique MCT value, depending on its size and shape.
So how do we actually use this MCT number? Well, here's the good news. Almost every trim problem you're ever going to face can be cracked with a super simple 3-step recipe. This is your toolkit.
It builds pretty logically. First, you figure out the trimming moment. That's the turning force that's being applied. Second, you use that MCTM number to find out how much the ship's trim is actually going to change. And third, you just split that change between the bow and the stern, because remember, as one end goes down, the other has to come up.
Okay, theory is great and all, but let's see how this stuff actually works in a real example. We'll start with the most basic scenario there is, just moving a piece of weight that's already on the ship.
So here's the situation. We've got a ship that's perfectly level. We call that being on an even keel. A crane picks up a 60-ton container and shifts it 80 meters toward the back of the ship, the stern. Our job is to figure out the new drafts.
Step 1, we need the trimming moment. This is pure high school physics. Force times distance. We've got 60 tons of weight, and we moved it 80 meters. You multiply those together, and you get a trimming moment of 4,800 ton-meters. Easy enough.
Step 2, let's find the total change of trim. We take that moment we just calculated, 4,800, and we divide it by our ship's special number. It's MCTC, which for this example is 150. The result? The ship's total trim is going to change by exactly 32 centimeters. And now for the final step. Step 3, we split the trim. In this case, the pivot point is right in the middle of the ship, so that 32 centimeter change gets split perfectly evenly. 16 centimeters for the bow, 16 for the stern. And since the weight moved aft, the stern sinks deeper, so we add 16 centimeters to its draft. The bow, of course, rises up, so we subtract 16 centimeters from its draft. And there you have it, our final drafts.
Okay, so that was basically the warm-up. Shifting weight that's already there is pretty simple. The real test for a ship's officer is when you're loading or discharging cargo, because that changes the entire weight of the ship.
So here's the million-dollar question. What happens when we actually add new weight to the whole equation? This changes everything, because now you've got 2 different things happening at the exact same time. First, because the ship is physically heavier, the entire vessel just sinks down evenly, We call this parallel sinkage. Then, after it's already sunk, the placement of that new weight creates a trimming moment that tilts the ship around its pivot point, just like in our first example. The key is you have to calculate these two effects, and you have to do it in that order.
All right, here we go, our boss-level problem. We have a 90-meter ship, and it's loading 450 tons of cargo. That cargo is being placed 15.5 meters forward of the ship's pivot point. The question is, what are the final drafts?
Let's just walk through the numbers together. First, we calculate that parallel sinkage, which turns out to be 45 centimeters. So boom, the whole ship sinks by that much. Then we calculate the trimming moment caused by putting that new weight forward, which tilts the ship forward. This gives us a total trim change of about 58 centimeters. We split that change between the bow and the stern, and then we apply it to the drafts we got after the sinkage. The result? A final draft of 5.169 meters aft and 5.253 meters forward.
And this brings up a really fascinating little rule. What if that pivot point, the LCF, isn't perfectly in the middle? Well, this quote from the source material gives us the golden rule. The end of the ship that is furthest from the LCF will experience the greatest change in draft. It makes sense, right? It's just like a lever. The longer side of the seesaw is always going to move more.
So why does any of this number crunching really matter? Well, this isn't just a math problem from a textbook. For a ship's officer, constantly monitoring and calculating trim is absolutely critical. It's about making sure the propeller is deep enough in the water to work efficiently, that the bow isn't just plowing through the waves, and that the whole vessel stays stable and, most importantly, safe on its journey.
So, we've seen how some pretty simple principles can be used to manage these absolutely immense forces. Now that you can balance a ship on paper, it makes you wonder, right? What other invisible forces do you think are at play out there, keeping these incredible engineering marvels perfectly poised on the world's oceans?